So 4.3, solving one-step equations. So I know what a solution to an equation is. That'll be important because sometimes we find values that are not actually solutions. And as it turns out, there's an infinite number of values that are not solutions. But there is one that will work. So it's up to us to be able to find the one. And I know when to force values to be ones or zeros, which I believe we've talked about before. So for example, when we create ones, we're going to use that anything divided by itself is one property. Or with zeros, that's like zero pairs. So if I have something, I can add its opposite. Or if I have something positive, I can just subtract it from itself to make a zero. And then I can force values to be zeros and ones with principles of equality. It's good. But again, it is also, so not only should we be able to make zeros and ones ourselves, we need to know when to do it. So what is a solution? A solution to an equation is a value that you can replace a variable with in order to make the equal sign a true statement. So it's saying the equation, that really is the equal sign. Because it's possible to see an equal sign, but it ends up being a false statement. So for example, if I saw an equal sign like this, and I said, you know what, 2 equals 2. Really, this is more of a question, right? And you got to be careful because sometimes people will give you equivalence statements like this one, but it is actually a false statement. So it's up to you to determine, is this actually true or is it false? So if I ask you, does 2 equal 2, what would you say? But yeah, 2 definitely does equal 2. That right there is a true statement. Now, of course, we understand, hopefully, that I could be like, now is it true? It literally is as easy as 12 definitely does not equal 2. So now you have a false statement. And of course, if I were to be like, okay, well, now I've changed it back into a true statement, right? Well, what we do in math is we can kind of start with this type of statement and say, well, 12 definitely does equal 12. But like we've said before, sometimes 12, I don't want it to be 12 directly. What I would like it to be is something like 10 plus 2. Okay, now this statement is still true, and that it's fine. It's still a 12 on the left side. I just changed the way that it looked. That's all I did. I changed the way that it looked. I didn't actually change its overall value. So if I did something like this as well, so if I said, you know what, we're going to take the 12 minus 5, and then we're going to plus 5 right there, I still did not change the value, or if that equal sign is true, right now, even though I subtracted and added 5 to the right side there, it is still true. Now here's what I'm going to do as well. Let's take that plus 5. Okay, so in fact, let's go back here as well. Okay, so see this 12? I got 12. Right now, this statement is false. But the question becomes, how can I make it true? Well, I would say probably just erase the minus 5. And then it's like, oh, it's pretty obviously true. But what I can do is I can just say, you know, I'll just do minus 5 right there as well. So with equality, what happens with an equals statement like this, if you want truthfulness, if that's what you want, which we do want in a math class, by the way, we want this to be true in the end. What I'm showing right here is if I do something to the left side, or even to the right side, I need to do it to the other side of the equal sign to maintain equality. Now again, sometimes that 12 on the left, maybe it doesn't look like 12. Maybe it looks like something like 10 plus 2. Now 10 plus 2 minus 5 is still the same and equal to 12 minus 5. Here's what we do sometimes though, because as math people, we're like, there's no letters, and we learn to love letters in math problems, and we want everyone else to love them, even though they hate them. So what we'll do is we'll say, we can look at this and we see 10 plus 2 minus 5, it equals 12 minus 5, and right now we declare it true because overall the value on the left is 7, and overall on the right the value is 7. But then what we're going to do, we're going to say, look at this right here. Oh, okay, now we're going to say we need this to be true. We need this equal sign to be true, but what would the value of x be to make it true? Well, if I wanted it to be true, just like we saw barely, you'd have to make the x a 2. Well, okay, that's how I get truthfulness. Again, like I was saying before, let's say I replaced x with 3. Would I have a true statement? No. No, what if I replaced, let's go with something pretty extreme here. Let's say I said x was 1,000,000. Is it true? Definitely not true. Okay, so the only value of x that will make this true is x is 2. Bam. And that's what we're saying right here. Well, on the assignment, it's going to say something like solve for x, or it'll just say something like solve. And if it does, it's really saying what value of x will make this equal sign a true statement. Because when you start out, so here's what it's going to look like. Usually you start out with something like x plus 5 equals 100. I don't know. Okay, but if it says solve for x, it's really saying please find the value of x that makes this true. Because there's 1,000,000 values that make it false. Well, there's actually an infinite number of values that make it false, both negative and positive, fractional and decimal, not that we care. But again, it just tells you that if you're going to gamble on this, because when I do my junior high classes, they're like, you know what, I'll just guess on all of them. X is 5. And it's like, okay, well, you have an infinite possibility of getting that wrong if you're not going to, unless it's C for some reason. I guess I don't know if I addressed that adequately. So finally, a solution, like down here, a solution is a value you can replace a letter with to make it a true statement. Because we have this whole statement right here. So this is a statement right there. X equals 10. We got to find a value that I can replace x with to make it the equal sign. It's to make the equal sign a true statement. Bam.
Can an x be?
So this one, though, if I were to take that x and replace it with 10, okay, so that's what I've done right there in red. Then it would show 10 equals 10, so I can have a question mark over my equal sign. Well, last time I checked, 10 does equal 10. That's a true statement. But 10 is the only value I can replace with x to make it true. Now, if you want to be smart and be like, well, what about 5 plus 5? Okay. We wanted to simplify it, so it's just 10. So, again, what is the solution of the following equation? Let's ask this question in a better way, in my opinion, anyways. So again, what value of x will make the equal sign true? So that's it. If you replace the x with 10, so I should write this in here, x plus 2 equals 10. If I were to take the x and replace it with 8, now, if I put a question mark over my equal sign, I can declare it true because I know that 8 plus 2 is 10. Now, here's the way that we usually write this, and this is why I did not do it on the last slide. But we usually would show the solution that x equals 8 as x is 8. So in other words, if I take the x from the original equation and replace it with 8, I get a true statement just like I did here. On the assignment, what they'll do is they'll say x equals, and then they'll put a box here. You just type in the 8 and it's good. I kind of like to just show it as, well, x equals 8. When I'm doing it by hand, just kind of box in the whole thing.
So when you write it out, like the answer?
Okay, here's a new one. Now you notice I'm trying to keep these equal to 10 because 10 is a fairly manageable number. So if I said this would read something, or x minus 3 equals 10. Again, the question becomes, what value of x what value can I replace x with in order to make this a true statement? Once you realize that x is not 7, then you're like, okay, then it has to be 13. Because if you were to take that x, and if you were to replace it with 13, then it would show 13 minus 3 does equal 10. I guess I should ask that like a question. 13 minus 3 equals 10. Yeah, that's true. Okay, so again, we would write the solution as x equals 13. We did it. Now, I'm not showing a specific mathematical strategy to solve for that x. And that's kind of on purpose, just so we can understand what we're actually trying to do here. We're trying to find a value of x. We're trying to find a value to replace x with in order to make it a true statement. And when I say it, I'm talking about the equal sign. Because if I were to replace x with anything but 13, like -8, this would be false. If I replaced it with -7, I'd get -10, which looks close, but it still is, it's false for this equation right here. Addition, subtraction, now multiplication. 2 times something equals 10. We need to know what that something is. What is the solution to the following equation? So again, the question is, what value of x can what value can I replace x with in order to make this a true statement? So if I replace that x with 5, I'm putting in parentheses so I don't have to show the multiplication symbol. And now that I think about that, the multiplication symbol would have been less work. But if I have 2 times 5, question mark over my equal sign, because I don't know if that's true, it is true. So these solutions, I just can't emphasize this enough, they're almost literally sitting on a razor's edge. Because the moment you drift anywhere from 5 in either direction, it is now a false statement. So you have, again, if you're going to guess, you almost have an infinite probability of getting this wrong, and pretty much a 0% chance of getting it right, if you're going to guess. But again, if you think about it, yeah, it is. Since it's a multiplication fact, yeah, we should know that 2 times 5 would equal 10. And that means that sometimes we can do this without any type of extra math strategy. A little bit different, I guess, but we got to find a value of x that would make this true. So what value of x will make this a true statement? Well, if you did replace this x with 40, now this is what our equation looks like, right? Question mark, because we replaced the value. Well, is this actually true? 40 divided by 4, well, last time I checked, it's 10. 10 does equal 10. That's a true statement for me. So now we know if you replace the x with 40, you get a true statement. That's all we want. Now, when we want to use a little bit more strategy with these, because sometimes we won't get something that just equals 10. It'll be equal to something weird, maybe something negative even, okay? That's when we look at what we call principles of equality. Now, principle of equality just means whatever you do to one side of the equal sign, you must do to the other side of the equal sign. Just kind of like I showed before with that 12 example, right? So if we start out with a statement of 12 equals 12, which is true by itself, but if we were like, you know what, I'm going to do something to this 12 and just say, you know what, I'm going to minus 5 to the left. Well, in order to maintain equality, we have to subtract 5 from the right as well. Okay, now, there's going to be more reason to just being like, we're going to subtract 5 everywhere. And that's where we come to, well, why are we going to be, or which one would I even use in order to solve an equation? So we start with the first two, addition and subtraction. So in addition and subtraction, and this if-then stuff is just a really nerdy way to say whatever you do to one side, you got to do to the other side. So like the A equals B, that's an equal statement. So if you add something to the A and add something to the B, it maintains its equality. This is true for all 4 operations, whether it's addition, subtraction, multiplication, or division. But again, we do these addition and subtraction if we want to specifically force a value to become a specific value. So we're going to use addition and subtraction in order to make zeros. Okay, zeros. Zeros are kind of an interesting thing in math, especially when we get to equations, because let's come back up here. Okay, so we've looked at this example before. We subtracted 5 from both sides, and you'd get 7 equals 7 right there. What you're not seeing about that equation is that there are lots of zeros being applied to that 12 minus 5, either side, by the way. And by applied, I mean, I'm going to say add. So that's a positive 12. So look, I can take that and add 0, and I can add 0 there, and I can add as many zeros as I want. But by adding 0, I don't actually change the value. So zeros, they're there, you just can't see them. These are what we call phantom zeros. Phantom, so that we don't actually have to look at this garbage. So I'm going to, if I can do this decently. There we go, okay? Now those zeros that I just erased, they are there. They're looking at you. They're watching always, which is why they're, phantom values are kind of creepy that way. They are there, and they'll always be watching. Zeros in math, we kind of treat like people that are zeros. It's like we just ignore them. And I know that sounds jacked up, but sometimes it kind of just hits home and helps you to remember it. Since we're going to make these phantom zeros so that we can ignore them, the reason why we're going to do that is if we don't want a value to be there. And it can be an x value, it can be an x term, I should say. It can be an x term, it can be a constant. I mean, those are pretty much the only two options we're looking at in this class. Okay, so there will be times to make zeros, and zeros, which become phantom zeros, the phantom values also apply to multiplication and division. And like we saw on the objective, we are going to force or make values ones as well. And the reason why we're going to make them ones is because then we get to ignore those too. Now we will ignore them, but they will still be hiding in the shadows watching, just like the phantom zeros will, which again makes those phantom ones a little creepy. Now specifically, when we make ones, generally speaking, but for the most part for us, we're going to make coefficients. Coefficients ones. Okay, now the reason why I want a coefficient of 1, and we talked about this last time, is because if I saw a variable x, I can ask, what is the coefficient of that x? And some students, just because we don't have a lot of experience with it, they may say, well, it's 0. It's not 0, because if it was 0, then I wouldn't actually have to show the x. But I do need to show the x. So the coefficient is the value that's being multiplied by the x. So the coefficient would be a 1. Now, because we couldn't see that 1 there, it used to be a phantom 1. For today, what I'm going to do is I'm going to keep those 1s there, so I'm not actually going to make them phantom 1s, so that we can actually see what the value is that we're trying to accomplish here, okay? Now, we're going to make zeros, we're going to make 1s for specific situations. Oh. Coefficients is a hard word. Coefficient, my bad. I'm not so satisfied with that, but I'm also not so embarrassed by it, which is kind of weird. So here's the thing. We're going to make zeros, and we'll make 1s. Today, we're looking at just one-step equations. They're called one-step equations because we should only need one of these in order to solve it, or to find a value of x that will make it true. This first slide, we're not actually going to solve any of these. We're just going to determine if we need to make a 1 or a 0 in order to solve it. Okay, now we know addition and subtraction will make zeros. Multiplication and division will make 1s. So pretty much if we see any of those options, then we should hopefully know which one to use. For example, this first one, now I see it being added to the x. You could really say it's subtracting 15 because of the negative right there. But either way, whether you see this as plus or minus, that means we're going to make, for this first one, I'll put it next to it. This one we're going to make 0. In fact, I'll make a 0. How about that? Okay, the next one, it's not showing the operation, but that's multiply. So that's 6 times y. Well, multiplication and division is when we make 1s. So this next one, we will make a 1. We're not going to make 1 yet, but that's what we would do. So again, it's just going to help us to determine which operation to use. The next one, x divided by 4 equals -1. Well, there's division right there. So since there's division, that means we would need to make a 1. And then the last one here is showing, again, you could say it's adding the x, but the 21's positive, so it's still addition. So for this one, I think I can save that. Make a 0. So we're going to solve this problem. It says x minus 58 equals -90. Now, the fact that it's negative, of course, we're going to have to go back to some negative rules, and that's okay. Not that that sounds weird. Okay, here's how I show my work with this. So I know that I'm going to be applying principles of equality. Now, that means that my equal sign, I can bring it down directly like this, but then I'm going to draw a line directly beneath the entire equation, so that I know if I do something, let's say I do something to the right side, then I know I got to do it to the other side of this line. This line helps me to keep track of the work that I'm doing. But since it's principles of equality, if I do it on one side, I got to do it to the other side. So for me, it's purely an organization thing. Do you have to do it that way? Of course not. I would never force you to do that. So some students, they'll kind of show it on one side or the other, and then they'll be like, oh, I'm good, but they tend to make more mistakes. Again, I'm not going to force you to do it. So on this one, what I see is a subtraction right here. It's minus 58. Since I'm looking at either addition or subtraction, I know I'm going to need to make a 0. So if I can just get myself to make a 0, then I will know what I got to do to the other side. Specifically, well, I guess before I get to the specifics, I look at this and I think, well, I'm trying to solve for an x, right? I want to know what this value is, and maybe some of you guys could do it in your head, and that's pretty cool. What I would like to see from my final equation is x equals just a number, meaning I don't want to see anything added or subtracted to this x, and that way I can write it like this, just x. But that means that the minus 58 there is going to have to become a 0. Now that term by itself, I'm going to write it all out, is negative 58, right? Okay, so I've got negative 58 of something. How do I make a negative 58 a 0? Add 58. So that's the opposite thing, right? So I see that these numbers match. It's just they're kind of opposite signs right there. Well, they are opposite signs, negatives and positives. Mm-hmm. But again, I applied this plus 58. I put that there, which means I need, since I did it on the left, I also must do it on the right. So that's what I'm going to stick with right here. Now that allows me to drop the x because negative 58 plus 58, this is, I didn't circle that because I just love them so much. It's because that's a 0. It's a value of 0 right there. And I do not want to put, I don't want to put down here, I don't want to put a plus 0 because then it creates more stuff to get confused about. But now, on the right side, here we got a little work, right? We got negative 90 plus 58. Okay, well, we're adding opposite signs. We got a positive and a negative, and there's more negatives than positives, so I definitely know that my answer is going to be a negative. We did make that 0, by the way. Since they're opposite signs, I'm going to take the big number, 90, and subtract the small one, 58. So we're going to make that 10 minus 8 is 2, and the ones place value, 8 minus 5 would be 3. Now applying that negative, which we already knew was part of the answer, boom, this is what we get. And what I can do now that I have this, because I feel pretty good about that. Like, hey, that was some good work that we did right there. We made a 0. But we also added some opposites, and that's cool. Or nerdy, either way, maybe both. But what I'm going to do now is I'm going to go back to the original equation, which was x minus 58 equals negative 90. Okay, what I'm doing right now is I'm going to check. So the reason why I'm doing this is just to make sure that my answer is correct. Because here's the thing is, if I can do this, and if I can do it right, which I don't always, but if I can do this right, then it's going to guarantee that I actually have found the solution. Because remember, the solution sits on a razor's edge. Anything bigger or smaller than the actual solution, anything in any amount will make it a false statement. But I need this to be true. So I'm going to check for truthfulness. I'm going to put a question mark over my equal sign by taking the x and replacing it with the value that we found, and that is negative 32. Now in this work, there's not really anything to do with the negative 90. That's good. But what I am going to do is I'm going to take negative 32 minus 58. It's a negative minus some stuff, which is just going to make it more negative. So that means we take the two numbers, 32 and 58, and add them together. So in the ones place value, 2 plus 8 is 10, carry the 1. 1 plus 3 is 4, plus 5 is 9, and we get negative 90. Hey, that's true. Well, we checked it. We found that the value of x that we found, x equals negative 32, was true. Now I feel better about boxing this in, and now just to celebrate, we'll call it a solution, because that's what it is. It's the only value in the original equation that makes it true. All right, negative 7 equals 4 plus x. Give it a shot. Well, that's all I'm going to do as well. So, yeah, right here, I'm looking at an addition sign, even though it's really that it's positive 4. So again, I know that I'm going to have to make a 0. And again, that's purely based on the operation that's being used. I'm going to make a 0. I'm going to make a 0 from that 4, because what I'd like is to take this x and just be able to make it by itself. And even though it's on the right side of the equal sign, it doesn't matter. So the 4, let's make it a 0 by subtracting 4. But if we do it to one side, we got to do it to the other side. Okay, so that does zero that out as planned. We planned that out. We forced it to happen, which is why there's reasons for rejoicing. Now that's not a division symbol, it's just an underline. So a negative 7 minus 4 is just going to make this more negative. And then how negative is it? Well, 7 plus 4 negatives would be 11 negatives, negative 11. Now, that should be good. But we can double check this, which I think is a good thing, because I can take the original equation, negative 7 equals 4 plus x. But I'm going to replace the x with the value that we found as negative 11. And then I'm going to put a question mark over the equal sign. Okay, so we're going to check to make sure that this is true. Nothing to do with the negative 7. It's just negative 7 equals something. And this would be 4 plus negative 11. They're opposite signs. There's more negatives than positives. 11 minus 4 is 7. So we get negative 7 equals negative 7. Yeah, that's true. And since it is true, now I can box this in with confidence knowing that I found the solution. All right, try this one. Negative 10 equals negative 16 plus x. So right here it says solve, which means please find the value of x that will make this equal sign a true statement. Because if I just said, you know what, x is 0, done, it's false. That's not going to do anything for us. Well, we want to find that value of x that makes it true. So I'm going to apply a principle of equality here. Now that arrow is going to bring down the equal sign. And once again, I have the negative 16 and we're adding the x there. Again, since it's either addition or subtraction, however you want to look at it, I know I'm going to make a 0. I'm going to make a 0 here, okay? So specifically, I'm going to make the 16 a 0. Sorry, the negative 16, because what I'd like to do is take that x and drop it. I don't want anything added or subtracted to it. Now, sometimes in the future, what you'll have is like 3 of those x's right there, and that's okay if you do. I just don't want that minus 16 or negative 16 with it, so I'm going to make it a 0 by adding 16 there. Now, you'll notice I didn't even write anything on this side because my focus is to make this a 0. Now that I put that there, though, I need to know that if I do something to one side, I must also do it to the other side. That's negative 10 plus 16. So just going through the rules here, we're adding opposites. There's more positives than negatives, so I know my answer is going to be positive. And you just take the big number, they're opposites. So you can take the big number minus the small one. 6 minus 0 is 6. 1 minus 1 is 0, so we end up with positive 6. Now I'm going to do the work on this, even though I'm not sure that many students really feel the need to do this with one-step type equations. I'm still going to do it, though, because, I don't know, I'm a math nerd and I probably enjoy it more than I should. But I'm going to take the x, and I'm going to replace it with the x value that we found as 6, and I'm going to check for truthfulness. So there's my question mark. So I know that negative 10 has to equal something. Hopefully, if we've done this right, it's negative 10. So negative 16 plus 6, they're opposites being added. There's more negatives than positives. So I know it's going to be negative, so the negatives match. You take the big number minus the small number. 6 minus 6 is 0. Drop the 1. It is negative 10. That right there is true, which means we did, in fact, find the solution. Which is, I mean, if you think about it again, there's only one value that would make this true. We found it. There's an infinite number of values that would make it false. We found the true one. So on this one, negative 24 plus x, just right there, we know we're solving for x. We're always solving for x. Okay, so right here, just because we got addition or subtraction, I'd consider it subtraction because we had to get rid of the negative 24, but that means I got to make a 0. And again, it's strictly because of the operation that's being used. Whether you want to consider it addition or subtraction, what I'd like from this is to take that x and just to be able to drop it by itself. The equal sign will always drop. I mean, I put that there now, I put it there earlier, it doesn't matter. But what I know is that I have to force that negative 24 to be 0. I'm going to make it do what I want it to do. I don't want it to take control of me. So I'm going to make it a 0 by adding 24. Again, I put this line here on purpose so that I can keep track of if I'm doing something to the left side, operations. Like dropping the x, I can't be like, well, I'm going to drop this x. There's no x. But the plus 24, yeah, I got a plus 24 on both sides. So that does 0 out. Negative 24 plus 24, that's a 0. We dropped the x already. Negative 33 plus 24, there's more negatives than positives. They're opposite signs. And we take the big number and subtract the small number. To make that 13 minus 4 is old 9er. 2 minus 2 is 0. And we get negative 9. Now the check. So 24 plus x, it should equal negative 33. That was the original equal statement. But now we're going to take the x and replace it with 9. Sorry, negative 9. Now, I mean, I'm not going to change that to a minus sign. I know that I'm adding the two values together. I'm going to make sure that this is true. But I got a negative plus a negative, so it's just going to become more negative. More meaning take the 24 and 9 and add them together. That's how negative the result is going to be 4 plus 9 is 13. Carry the 1. 1 plus 2 is 3. So I end up with negative 33 equals negative 33, which is true. Since it's true, we did in fact find the solution. So negative 54 equals 3x. We're just underlining because we chose those values. But I'm planning still on using a principle of equality to bring down the equal sign and the x. The problem right now is I've got 3x, or, and this will be important so that we know what we're trying to make, because we only have two options, zeros or ones. This is going to be 3 times x. So as of right now, the 3 is a coefficient of x because it's being multiplied. Since I'm using multiplication here, this means I need to make a 1. Now I'm going to show this a little bit different than last time because the last few examples we were just showing an x. But I specifically want to show this as 1x so that we know we're actually trying to accomplish or change a 3 into a 1. Now, because we're doing this, it's not, well, I know how to make a 3 a 1. But, again, this line is telling us we're using principles of equality, so if I do something to one side, I must also do it to the other side as well. So I'm going to take that 3, and how do I make a 3 a 1? I just divide it by itself. Because anything divided by itself is 1. And that means if the 3 were negative, I would divide it by negative 3 instead. But it's positive, so I'm dividing by positive 3. Now that means I've got to take the negative 54 and divide it by 3 as well. Okay, so a little bit of work here. I'm not worried about the negative because I got a negative divided by a positive, or just one negative makes the answer a negative. However you want to look at that. But I'll have to take the 54 and divide it by 3 because I don't have my 3 multiplication tables memorized up to 54. So starting with the 3 and the 5, I know 3 goes into 5 once. 1 times 3 is 3. So we have 2 remaining there. We'll drop the 4 to make it 24, and 3 will go into 24 8 times. 3 times 8 is 24, and that does exactly what we wanted it to do, to have a remainder of 0. Now that quotient 18 is our final answer right there, but with the negative sign. So x should be negative 18, and if you wanted to say, you know what, I just want to write it as negative 18 equals x, that's fine. It's like, both of those are going to get you full credit. Okay, now that should work. It should work, which means I'm going to check. So I'm going to take negative 54 and show that it equals 3x. I want to show that this is going to be true if I replace the x with negative 18. Okay, so that'd be negative 54 equals, and now I got to do 3 times negative 18. One negative multiplied there is going to make the answer a negative. 3 times 18. 3 times 8 is 24, carry the 2. 3 times 1 is 3, but adding the 2 is 5. Pretty much we just did this long division backwards, but applying that negative makes it negative 54. Well, that's true. And since it is true, that means that we did in fact find the solution, either way that you wrote it. Yeah, try this one out. Solve negative 7x equals 56. Try it out. So, on this one, once again, I see that we're multiplying between the negative 7 and the x. We just want the x to be by itself or to be a 1x. So since we're doing multiplication there, I know I'm going to have to make a 1. Which again is purely based off of the operation being used. So, I got a negative 7x. What I would really like out of this is to have it just be a regular x or 1x. So I've got to make that negative 7 a 1 simply by taking it and dividing it by itself. But if I do it to one side, and that was a negative 7, which is okay, I got to do the other side. So 56 divided by negative 7. Now there's only one negative being divided, so I know the answer will be a negative. And then 56 divided by 7 would be 8. So the last step, as usual, we'll be checking. So negative 7x equals positive 56. I don't know if this is true or not yet, but I'll replace the x with the value we found as negative 8. Then we'll check for truthfulness. So this should equal 56. Well, negative 7 times a negative 8. Negative times a negative will be a positive. 7 times 8 is 56. That's true. So we did find the solution. So for this one, we have an x divided by negative 4. Now, we know, just right now, since we do see division there with the fraction line, that's a division sign, that means I'm going to need to make a 1. Now, usually I take that negative 4 and be like, well, we just divide it by itself. Yeah, but we're already dividing as part of the problem there. So I'm going to use the principle of equality, but I'm going to make this a 1x. Maybe not in the way that you'd think. So what's going to happen here is we're going to go back to fraction multiplication a little bit. The truth is, I'm not really going to show the fraction multiplication in the beginning, because in order to make that negative 4 a 1, which I do want, I would take it and then I would multiply x, the whole part of x divided by negative 4, and just multiply it by negative 4. Now again, I put that negative 4 there on the right, which means I would also need to put it on the left as well. And is that going to make 1? Yes, it is. I usually show that the 1 just kind of diagonal like this. It is a 1, it's just, I've crossed them out with a 1. And that's where this one comes from. Well, how does that work? Well, here's how it works, is we had x divided by negative 4. What I did is I multiplied it by 4, and again, you don't really, well, I multiplied by negative 4, like this. And I'm specifically putting it right there because it would be negative 4 over 1, which if we were to use cross simplification, I could say, well, you know what, this the negative 4s, I can simplify by dividing them both by negative 4. And then, well, that would be a 1 right there. And then this one also would be a 1. Now, really, all I got is x times 1 and then a 1 times 1. X over 1 would be x, or 1x, either way. And you could say that's the 1x right there. I don't like to show that in here because it's a lot more work than I like to do, and it tends to confuse people. So, if we can just understand, if you have it divided by -4, in this case, then you just multiply by -4, again, on both sides, and then you'll have your answer. So we need to do the multiplication, and, well, it's a negative times a positive, so that'll be a negative. Then we got to do 37 times 4. So 4 times 7 is going to be 28. Carry the 2. 4 times 3 is 12, but add the 2 is 14. So it ends up being negative 148. That should be our solution. We can double check by taking 37 and making sure that it equals x over -4. We just found that the x should be negative 148. So this should end up being 37, and it's two negatives being divided, so we know the answer will be a positive, and we can show the division. So that'll be 148 divided by 4. 4 will not go into 1, but it will go into 14 3 times. 3 times 4 is 12. We got 2 left over in the tens, drop to 8. 4 goes into 28 7 times. 7 times 4 is 28. Nothing remaining. So we end up with 37. That is a true statement, just like we expected. And so of all the values that could have been false, we found the one that was true. So we did find the solution. All right, try this one out. So yep, on this one, I'll just show the work here. What we want is a 1x equals something. We don't want x divided by anything, so to take away that division and make it a 1, we're going to multiply both sides by -4. So yeah, that makes a 1 right there, and then over here on the right, -3 times -4. Negative times a negative is a positive. 3 times 4 is positive 12. That's it. This one's a b, it's not an x anymore, which will happen sometimes on the assignment. It doesn't matter if it's an x or a b or an a or a z or a y, it doesn't matter. We just know we've got to find a value of b that will make this true. Now, looking at this, though, a lot of students make the mistake of just saying, well, b is going to be 148. Well, that can't be the case because of the negative in the front. So what we're going to do is we're going to treat this as though it were a -1b. Okay, because there's that phantom 1 right there. What we really want out of this is a 1b instead, positive, not negative. And yes, the -1 is being multiplied by the b, so we know that we are actually trying to make a 1, which guess I kind of jumped the gun there. But how do I make a -1 a positive 1? Simply take it and divide it by itself, just like you would any other value in order to make it a 1. But if I do it to one side, I need to do it to the other side as well. So on the left, I've got a negative divided by a negative, which is positive. 1 divided by 1 is 1. On the right, 184 divided by negatives. That's positive divided by negative, which is going to make the answer a negative. And then in 184 divided by 1, anything divided by 1 is itself. We get a 184 there. And again, without necessarily going in and fully checking, I know it's -1 times negative 184, and the two negatives is why this becomes a positive 184. That's all we got. So again, a solution to an equation is a value that you can replace a letter with to make the equals sign true, because there's a lot of them that'll make it false. And then we know when to force ones or zeros. Again, ones would be for multiplication or division, zeros for addition or subtraction, and now we know how to make zeros and ones with principles of equality. So today, it's only one-step equations, which require only one operation. But in the future, I assume next time, they'll be like, you got to use 2 now. But it really is just going to come down to, can we make ones and can we make zeros? Because if we can, we could do this with 10 or 20 steps if we needed to. But usually we don't need more than 3 overall anyway.